We want to look at uh, the refraction of light. And then, of course, later on, we're going to look at how light is refracted as it passes through a lens. So this is another behavior of light we want to study. We talked a lot about reflection and how light is reflected in a mirror, how the image and so is formed. So what we want to turn our attention now to is the refraction of light. Just what really, when we talk about the refraction of light, what we really mean, right? So I know I haven't put in the word, the entire thing there. I just write 1 second. My pen seems to be giving me some, I hope it's not like. So, yeah, that's it. So, yes, I'm really talking about the refraction or light, right? Yeah. Now, just what really is the refraction of light? Well, what scientists have found is that when light passes from one medium to another, what can happen is the light can slow down. The speed of the light can actually slow down. And because of this slowing down, right, the light can actually, let me use the word loosely, the light actually bends or deviates from the direction it was going by a small angle, of course, right? So that's what refraction really is. It's the slowing down of light as it moves from one medium to the next, right? As I said, because of this slowing down, there is a slight deviation from its path, slight, if I'm to use the word, little bending, right? In that the ray doesn't travel, in that same straight line, it now moves away, right? In another direction. So before we go into it, we'll use some diagrams and so to illustrate what we're talking about when we speak of the refraction of light. But before we get into that, we just want to define something called the index of refraction, right? And basically, this index is given by this formula here, right? N equal the speed of light in a vacuum over the speed of light in whichever material we are talking about, right? And sometimes you can have light, let's say you have a body of water, light travels from the air to the water, right? You will have what we call the refractive index, right? Of course, we're talking about a vacuum here, right? That's really the reference light. Speed of light in a vacuum as compared to the speed of light in other materials, right? And given by that formula C over V. So, of course, this little table here, as you see, you can see this table. Is it large enough? Make it a little bigger. Can you see this table?
Yes, sir.
So this is what we call the refractive index. Of a number of substances, right? And they compare it with, I think the reference material is light in a vacuum, right? The speed of light in a vacuum. So you see diamond, right? It's 2.419. Glass, right? Then we have ice, all these, substances. So, okay, let's take diamond. Let's take diamond. So the refractive index of diamond is 2.419. I think you should whip out your calculator now. Equals to, what's the speed of light in a vacuum? Anybody knows? Well, there's no need to put the unit, right? Is that right? 3 by 10 to the 8th, thereabouts?
Yes, sir.
Speed of light in diamond. Right? So if you do some, calculation, the speed of light in diamond will be 3 by 10 to the 8th over 2.419, right?
Yes, sir.
You have a number for me? How would it be roughly?
I got 1.2 times 10 to the 8.
1.2 times 10 to the 8th.
Yes, sir.
Right? So it's a lot slower, meter per second, that is, right? Yeah. It's a lot slower. And you can understand why. Because diamond is a very hard substance, and hence it will oppose the movement of the light. Right? Because that's basically how that's one explanation as to why there's that slowing down, and it actually you remember we talked about that theory where they're saying that light is possibly a particle called photon, right? There's this theory that light behaves like a particle, it has a certain amount of energy, and as it passes into the diamond hard, the atoms in a diamond are so tightly packed, it opposes the photon, right? And therefore are slowing up, right? Yeah. So you notice that in air here has almost a refractive index of roughly 1, right? Most of the gases roughly 1, just like vacuum. Meaning the speed of light in air is almost the same as the speed of light in a vacuum, right? I said almost, I didn't say the same, right? So do you get that? Simple definition of the well, sometimes instead of saying index of refraction, you hear people say refractive index, right? Some people say that. Some textbooks and so use the phrase refractive index or the term refractive index instead of index of refraction. Good. So we come to something called Snell's law. Let's see if I can make this a little bigger. Diagram instead. Right? Can you see this well? So this is a man who Snell. He actually studied, uh, angle at which light, is incident on a material and how it's bent or refracted, right? And he came up with this law. Right? He came up with this law, saying it with is it here, right? Where if you have two materials, right, the refractive indices of the two materials and the sign of the angle that is made between the ray and what we call the normal is related according to this equation here, right? It's related according to this material, this equation here. Some textbooks don't put it like this. I think some textbooks put it like this. N1 over N2 equals the sine theta 2 over sine theta 1. I think that's how some textbooks put it. So if you open some textbooks, you'll see it written like this and not like that, right? This you might not see that. And just to say, well, okay, what's it? Well, we just talked about refractive index, right? That's what N1 is. That's medium one. Like if it's air, let's say the ray is coming from the air, you know, it's passing through the air. And then N2 might be water or glass or perspex or a piece of diamond, right? Whatever. So look here, if you look at the diagram, maybe what we could do is make this a little smaller, right? This up with it, right? So here, this is the like a torchlight, you know. So the incident ray comes here, right? I wouldn't say it's a torchlight. Let's say there's a pinhole there, like, you know, and a single ray comes down here. This vertical line here that makes a right angle with, well, in this case, they're using water, right? This line is called a normal. So when the ray hits there, there's some reflection, right? The water acts very much like a mirror. And you know when you watch your face in the water, you see some of it. But you don't see your face as bright as it should, right? It's not so when you watch in a body of water, your face is not bright. And the reason why is that most of the ray is not really refracted, right? Or let me not say most, let me not put ourselves in that situation. Some of the rays reflected, while some is refracted, right? So this is the angle we're talking about. Angle that the ray makes with the normal, and the angle in here now that the refracted ray makes with the normal. That's the relationship we're coming to here. This relationship here, or that relationship here, right? Then Snell found out that from experiments that the product of the refractive index of one medium by the sine of the angle that the ray makes is equals to the product of the refractive index of the other material times the sine of the angle it makes with the normal, right? So you're seeing that. So N1 times the sine of this angle is equals to N2 times the sine of the angle that it makes with the normal there. Those two products are equal. Right? And of course, the reverse things here. Notice in this diagram, if you were to point a light out here, you will have a bending away from the normal, right? While here you have a bending towards the normal, right? So here, as the light passes from air into the water, there is a slowing down. But here, as the light passes from water to air, there is actually a speeding up. right? There's actually a speeding up. So do you follow that little explanation there? Let me know, as we go along. I'm hearing people saying nothing. Let's look at a simple example. So you're determining the angle of refraction. So they're telling you here that a light ray, it strikes a boundary, air, water, right? Just like the previous diagram we had. We can actually draw that diagram in just a moment, right? So, there's, I think I should make some space for that. When I do this, you're still seeing the.
Yes, we see it, sir.
So let's say this is the water surface, right? And this is air. So we're gonna draw it our normal, right? And they say that the a light of ray strikes the air water surface at an angle of 46 degrees. So okay, the ray comes down here, right? And it makes 46 degrees here, right? And then, well, they give you the refractive index of water. And they want you to find the angle of refraction when the direction of the ray is A from air to water. So it's coming in from air, and it's going to do a little bit of bending there, right? So good. So it's going through there. So this is air. This is water. All right. Clear?
Yes, sir.
So air, we're going to use 1, right? 1.00 as the refractive index, and the index for water is 1.33, right? So we know that formula. Remember the formula. What was it? N1 sine theta 1 equal to N2 sine theta 2, right? So we know N1 is going to be 1 times sine of 46 degrees equal to N2 is 1.33 times sine of theta 2, which we don't know. Right? So that's what they did. So they rearranged this, and they found that sine theta 2 equal to 0.54. I don't know, you all are doing that fundamental maths course, so you should know that to get the angle, you sine inverse 0.54, and you get 33 degrees. And that means that this angle here is 33 degrees, right? Simple as that. So that's that first part. There's going to be a kind of little bending of the light ray there, a deviation from its original angle from the normal layer. And of course, the other part, if you're going from water to air now, so in other words, now this is your water surface, this is your normal. So you're going from this, going from here. So what are they saying? They're saying this is 46 now, right? So when it goes out into the air, there's going to be what will happen? The angle will get greater, right? So it will speed up this way. So that's your the other angle that we don't want, theta 2, right? So from here is 1.33, 1.33, this one is 1.00. So again, you use the same formula, right? Remember, you're now switching around, right? N1 is now 1.33, right? Now N1 is 1.33, not 1 anymore. N2 is going to be the 1.00, right? And theta 1 is going to be 46. So you do the necessaries there, and you get sine theta 2 being 0.96. Sine inverse of that is 74 degrees. Right, so theta 2 is 74 degrees, which we expect that. It's going to be a speeding up. It's going to move away from the normal. You follow the example?
Yes, sir.
Should be hard for you. A little bit of mathematics, but yeah. And oh, just one thing. Um, yeah. This is a nice little example, a practical example of, a little boat or yacht. It's looking for a chest, right? There's some indication of where the chest is, right? They have maybe the coordinates based on previous dives, right? So they want to know, well, okay, if the yacht is 3.3 meters up in the water there, right? How will it, direct the light so that it will point straight to the chest, right? So let's see. So they give you some details there, right? You all know a little bit of trigonometry. So here, this depth here is 3.3, and this distance here, right, is 2.0 meters. Do you know how you can be able to find this angle in here? Theta 2, using the tan ratio. Okay, tan ratio here. Okay, tan ratio. So it's like you're taking out that little triangle. This is 3.3, and this is 2, right? So this angle up here, opposite over adjacent, right? So tan theta 2 is going to be equal to 2 over 3.3, right? So where is it? So theta 2 then is going to be equal to tan inverse, right? Tan inverse of 2 over 3.3, and they tell you it's 31 degrees, right? So again, you know the refractive indices of water and air, right? So you just have to find theta 1 now. That's what they want. Theta 1. Right? So they found it here as 44 degrees. So all you got to do now, if I'm to blow that part, if this is where the torchlight is mounted, right? The torchlight is mounted there, this angle, for example, this angle here should be, what is the angle? 44 degrees. 44 degrees. Right? And you can see that's a Z angle, right? If you watch here, theta 1 is also this angle here. Right? As if you were to project this out, the normal is supposed to be a vertical line. If this angle is 44 degrees, then that angle is 40 using the Z angle like there, right? Do you follow this example?
Yes, sir.
A little bit of trigonometry that you should have picked up from CXC and so on. I want to move this over here. So let's see. This is something we observe very often. I don't know if you ever looked in a pool of water and the pool appears shallower than it really is. And so you don't run and jump in a pool of water like that. Right? It appears that that way, right? So like the situation with the yacht looking for the chest. If the water was clear enough, you will see that the chest appears to be up here, right? It appears to be up here because, again, of the geometry of the rays that are coming from the chest. So as light hits the chest and is traveling towards you, the chest is going to appear to be at a shallower level, right? As a matter of fact, the whole thing is going to look shallower. And that's what you're seeing here, right? Same thing if you watch from the top. Lots of times you go into a pool of water or you look into a pool of water and it actually appears shallower, right? So there's actually a relationship. Have you ever noticed that? That a pool of water appears shallower than it really is?
Yes, sir.
So here is a good formula to help you to see, well, what's the apparent depth, right? If, as a matter of fact, you can actually calculate the apparent depth if you were to know the real depth, right? And the refractive index of the two medium, right? Whether it's air and water or so. So this is a formula connecting the real depth with the apparent depth, making use of the refractive indices of the two medium. Most of the time you're talking about water and air. You can also talk about air and what else? You might be looking into what? This is a container containing some clear substance, methylated, oil, and so on, right? So remember this formula, good formula to remember to calculate apparent depth and so on. We're going to look at an example here, right? So let's see if we can get this example. I think this maybe it's going to be big. Maybe it's small. So you can see this one well?
Yes, sir.
So they say that a swimmer is treading water with her head above the water at the surface of a pool 3 meters deep. Right, so she's like swimming in, you kind of swimming in the water, and your head is just above water, right? So she sees a coin. Now the pool is actually 3 meters deep, but how does it appear to her? How does it appear to her? Right? How deep does the coin see? Right? So we use that formula right over here. Oh. So we use this formula here. We know the actual depth of the pool, right? Her head, remember, is in the is above water, right? So that's it there, right? And the refractive index of the water itself is 1.33, right? Oh, don't forget that the ray is coming from the water. Coin is down here, right? So the ray is coming from here and going up to the swimmer, right? Who is up here swimming. So it will appear when it bends and it goes like that. So it will appear down here, right? So that is why they're using N2 as the air. N2 is air, right? And N1 is the water. Keep that in mind. N1 is the water. Notice how they, right? N1 is 1.33, N2 is that. Just be careful of that. And you see that the calculation turns out 2.26 meters. So what happens there is that the coin appears to be a little shallower, right? So if it's a gold coin and you know, let's say 3 meters, you all know what is 3 meters? 3 meters, you're drunk it inside, right? 9 feet, roughly. So if you see the coin, you say, oh God, watch, I'm get rich now. And you're plunging because you think it's 2.6, 2.26 where, you know, let's say you're tall. You say, man, all right, I'm 6 feet. I can make it. No, you just drunk it because the coin fool you. Right? All right. So let's talk a little about another thing that is very, very useful. Very, very useful. Something that happens as light rays move, well, in a particular medium, in different medium, right? Something called total internal reflection. Right? Very, very useful thing. If you're having fiber optic internet now, what do you call it? Fiber. And you'll see in just a moment how that works. Right? Now here, if you have a ray passing through water, now a part of the ray is reflected, and a part is refracted. Now, if you were to increase theta 1, here, theta 1, you were to increase this angle, increase it now, right? You come to a point where the refracted ray actually is now parallel to the surface of the water, right? Now, when that happens, this angle here, theta C, is what we call the critical angle. Critical angle. And every material will have what we call a critical angle, where anytime after that, where the incident ray, if theta 1, right? The incident ray, theta 1, is greater than theta C, right? Which is the critical angle. Something called total internal reflection happens. So in this first instance, you do have a refractive ray up here. In this instance, the refractive ray is just where anybody up here will not be able to see it. And here, when the angle of incidence, notice it's greater than the critical angle, notice, right? is greater than theta 1, is greater than theta c, you have what we call total internal reflection, meaning all the light is reflected right back into the water. Right? Now, what's the use of that? What's the use of that? You will see. Well, let's see. You're following this total internal reflection thing?
Yes, sir.
I might have to make this a little smaller. Yeah, we're giving you an example. Let's do the example, then I'll go to some applications of it and so on. So they're telling you a beam of light is propagating through diamond, and in just a moment, I'll show you why diamonds sparkle so much. Right? It is because of what we call total internal reflection. When light enters a diamond, it doesn't escape. It bounces it around in there because of internal reflection. And the diamond sparkles. And that's why the girls, Joshua prepared to buy a diamond ring or a diamond earring for the girl that you will eventually, court or marry. Right? There's another boy in the class too, right, Daniel? Prepare yourself, the girls like diamonds. Yeah. So they're giving you an example here that a beam of light, it's propagated through the diamond, it goes in there, and it strikes the diamond air interface at an angle of 28 degrees. So they're asking you a few questions. Will part of the beam enter the air, or will the beam be totally reflected at the interface? Right? And then they're telling you, well, repeat part A, assuming the diamond is surrounded by water instead of air. Right? Good. So the reasoning says the total internal reflection occurs only when the beam of light has an angle of incidence that is greater than the critical angle. Right? So they say the critical angle is different in parts A and B since it depends on this ratio, N2 over N1. Right? The two refractive indices of the material. Because without air diamond and water diamond, right? Good. So first one, did they tell us about the 24 degrees? All right, we found we have to find it here. The critical angle is the ratio of N2 over N1, right? That's usually the ratio over N2 over N1. So air to diamond, that's the ratio. So it's equal to, when we find sine inverse, I get 24.4 degrees. So this here is the critical angle of what we call a diamond to air, right? Air to diamond, sorry. So the fact that the angle of incidence is 28 degrees, you're going to have total internal reflection. See? You see that? They say that the angle of incidence was 28 degrees. So the fact that the critical angle is 24.4, it means that there's going to be total internal reflection, right? And that's what we see here. Now here it says, if water rather than air surrounds the diamond, the critical angle is going to be 33 degrees, right? And if that comes from this relationship here. Now, because the light is incident on at an angle of 28 degrees, well then there isn't going to be total internal reflection, right? And you're going to see, well, the light, the diamond wouldn't sparkle as much, right? When you watch it in here, it's going to sparkle a lot because you have light bouncing around a lot in here. But because in the case, if you put the diamond in water, there isn't going to be total internal reflection. A lot of light is going to escape now, the diamond. And what you're going to have is the diamond will look, well, less valuable, less sparkling, right? And I think they have a little, okay, this is the one here. If the diamond is in air, right? If the diamond is in air. So if the light goes in, it goes in there, and it doesn't come out because the light is the angle of incidence is greater than the critical angle. So the light is going to bounce around here a lot, right? And that's why you have that sparkling look, you know, that diamond. But that's just, you know, jewelry. But you have this whole idea of total internal reflection being used a lot in some instruments and so, you know, like the binoculars, right? Some of you see, look here, the binocular down here is where you put your eyes. But then the glass through which the light enters is up here. How did the light reach there, right? Well, what's happening is the light passes into this glass here, goes into what we call a prism, right? This is what we call a prism, right? So the light comes in, look here, the light comes in here, totally reflected there. So it goes in there, it's reflected inside there. It hits there, comes back here, and then it comes out. It goes to another one now, look here. It comes in, comes in here, bounce across there, and then come out here. And that is what you see. Well, of course, they've put here now a little, what you call it, a lens, right? For you to be able to see the object that you're watching for from a far distance, right? So you see them make use of total internal reflection, right? In a prism. As a matter of fact, in telescopes too, sometimes they make use of that. And then this is the one I was talking about, the fiber optic cable now. The fiber optic cable that brings internet to your house. It's really a glass. It's a glass filament, you know. It's a glass filament. And the refractive index like is such that, well, the light is going to be totally, there's going to be total internal reflection in that glass filament. So no light is going to escape. So what they do, they take all the data, everything that you want to send across the internet, right? And they encode it now. Basically, what the little machine does, takes the data and changes into a certain frequency of light. Right? This is really going to tell you high science. It's the peak of human achievement of this, right? So what it does, it changes the data into a certain frequency of light. As a matter of fact, thousands of beams of light is traveling through this thing, but none is interfering with the other. They're all bouncing around in here and coming to you as well as going back. Right? So when you see you are using the internet and you have what you call fiber, GTT fiber, that's what is happening. Data is changed to light, right? A certain frequency of light, different frequency carry different pieces of information. And it's fed into this this fiber optic cable. And there's total internal reflection. So the light, as a matter of fact, if you were to watch into that fiber optic cable, this side it can damage your eyes, by the way, right? That light that is coming through would actually come out here. And then you put it into the modem, you know, the modem that you have at home there, and that modem takes the light and decodes the information, right? And it goes into your computer, right? Which actually processes it and so, right? And you have your information. Another application for the medical people, I know this little gross image I'm showing you here. For those of you who are working at the hospital and so, you probably know of doctors using instruments like these, right? Where they can look into your body, right? You see, they talk about a colonoscope, right? And you probably heard of colonoscopy, right? So inside your colon, there are these little things that are growing there. How do they know that? Well, they have to send in something, right? They just send in a little tube, and at the end of the tube, right? They have a little camera and all that, right? And the camera would take the image and bounce it around, you know, the light that is bringing the image, it bounces around on a fiber optic cable, right? Like this doctor is doing here. And he can watch here now and actually see. You see, he can't see the lady nose, right? But this object, this instrument here is allowing him maybe push that thing down till into her lungs. Look at that. And see what's happening. Same thing with they put it through the anus and it goes into the colon. And they see this little polyp, they call it. Maybe the thing is cancerous. So they go in later on and cut it off. Right? And so that's a medical application of total internal reflection that is going on in fiber optics. Right? Let me remove the image. I know it's disgusting. Anybody ever did a colonoscopy? Huh? Everybody ashamed. I've never done one, but it's a very shameful procedure. But it could save your life, you know. Where they put in a little tube into you and they see what's going on in your colon, all over in there. Good. So you follow so far? You following me so far?
Yes, sir.
Next, we want to talk about the dispersion of light. Right? The dispersion of light. And this is another thing where what happens, and sometimes we don't even think about it. White light as we know it, we think of it, you know, as just a single ray of light, but really and truly, white light is made up of several frequencies of light. It's not one light, it's several frequencies. You get plenty rays within that one white ray, right? And what happens is that within white light, every frequency of light within white light bends at a different rate, you know, or a different angle as it passes through, you know, different medium. Like you see in the diagram here, when the light passes through, well, I give you two of them, red and violet, right? So when it passes through a prism and it bends, because both of them will bend, remember we talked about that, right? It's going to be refractive, but guess what? Red doesn't refract or bend as much as violet, right? And using that, they're able to actually They're really able to split white light into its components, right? And that's how we get those rainbow colorings, right? And that's actually what's happening here, right? That as the sun, the ray hits water droplets at different altitudes, it's going to kind of reflect the light, refract it, and so on. But guess what? It's going to break up the light into its component frequencies and reflect and refract it at different angles. And what is going to happen? Well, you see the what you call the rainbow, right? Roy, chi, bill, red, orange, yellow. What is it? Red, orange, yellow, green, Roy, chi, bill. What is it? Blue, indigo, and violet. You all remember that? Right? And that's how you see the rainbow as you see in this picture here. Right? So distortion of light happens because, as we said, different frequencies within white light. As a matter of fact, different lights might have a light might be yellow, but guess what? Inside of it has several other frequency of light. So keep that in mind. So like white light has all these other wavelengths inside, right? All the other from red right down to violet. A little bit, and that explains the little rainbow. So you can go on reading about rainbow and all of that. Good. So do you want to take a little break? And then we go on to lenses? Huh?
We can, sir.
All right, let's take a short break. Okay, so we want to now turn our attention to lenses. Talk a little about converging lenses and what we call diverging lenses, right? So here, if we were to take two prisms and we were to pass light through them, okay, the light is going to be refracted in a way, to form these rays here, right? So the idea is to, okay, what about if we were to, instead of using two prisms, just have a lens, we eventually call them lenses, in the shape of, as though it's like, well, a flattened pair of prisms, right? And this is what will happen. They call these here, the shape of this one we call converging lenses, right? And the reason why is that a lens that is shaped like this actually takes these rays and make them converge as what we call, at what we call the focal point, right? So that is what converging lenses do. They take rays, incoming rays, and they, they focus them, and they pass through what we call the focal point, right? And of course, the length from the center of the lens to the focal point, called the focal length. And you'll see the use of all of that in what we call the lens equation. This here is the opposite, diverging lens. Very much like you take two prisms and you put them in that shape. And what happens is that the light is refracted, sorry, in a way that it actually, instead of going to a certain focal point, no, actually kind of spreads out the light more, right? As you see here. So if you have a set of rays incident on a diverging lens, well, instead of the light converging at a point, actually diverges. Right? Of course, if you were to pass some light, well, to get the focal point, notice how they actually project these lines to get the focal point here, right? Good. Now you're wondering, well, how do we draw the lens? What you call the ray diagram? How can we draw the ray diagram? All right. And this is basically how you draw it. Notice converging lens. Let me make this a little bigger. You can see that clearly. So
Yes,
you
sir.
have an object here. Notice that the object in this case is a little further than the focal point here, right? And maybe in your own time, I want you to try when the object is near is between the focal point and the center. When it's between the focal point and maybe two times the focal point, and even beyond, you can try that. So how do you draw the ray diagram? Notice the first ray you draw from the one point here to the center of the lens, and then through the focus, right? This one, right? Then notice here they draw from the top here straight through the focus to the center of this the lens, right? And then parallel to the what we call the principal axis. And the last one you draw from here straight through the center of the lens across here. And where these three here, this ray, and this ray coincides, right? Well, that's going to be your image. Right? Similarly, look here. You take up, this is a diverging lens, all right? You draw a ray going from the tip here to the center. But remember, you're not coming down to the focus, but you're taking from the focus here, going up. Remember, the ray is going to diverge and not converge, right? Here, from here to the center, and then it's going to go parallel. You're actually drawing it towards the, no, this is not the center, sorry. This is to the focus over here. Just like over here, where is it? This one here. How you go from, where am I? How you draw it from the top there through the focus. And here, you're not drawing it through this focus, but the one over here. But when it reaches the center there, you go parallel to the principal axis. And then the last one, you go from the tip there through the very center of the lens, right across. And where these three rays meet, that will be your image, right? I think this is the only way you can actually do this is if you actually do a drawing. And maybe we can do an exercise like that, right? So let me just go down here. This is like the rules, like you know, how you draw the three rays, right? It says this ray, the first one, travels parallel to the principal axis. In passing through a converging lens, the ray is refracted towards the axis and travels through the focal point on the right side of the lens. So let me go and see that. So you drop parallel to the principal axis. This is the principal axis. Goes to the center there and then through the focal point, right? Go back here. It says the second ray now passes through the focal point here onto the left and is then refracted by the lens in such a way that it travels parallel to the axis. So it goes down and then it goes parallel. And the third ray travels through the center as though, you know, there's no bend. right? And you follow the same rules here for this one. And that's how you will construct your image. Maybe we'll have to do a little exercise, and this is an example of one. Okay. So you have this object here. All three rays are here. Notice? You draw this one, parallel, goes there through the focal point. Draw this one, straight through the center. That was ray 3, and then ray 2 was through this focal point to the center, right? And then parallel to the axis. And here is your image, right? There is your image, right? Notice in this case, the object is well beyond the two focal length away from the lens, right? And you notice that the real image end up very small. And that's how basically cameras work, right? So you take big objects with your camera, you look at your size on the camera on your phone is so small, right? And here it is. So this is the idea where your object is well beyond two focal lengths from your lens, right? And that's what is used in a camera ray. So this is a real construction here, right? What you must do in your own spare time, and I hope you will do it because you might very well be tested on it. Put an image between two focal length and one focal length. And then even try one between here and tell me what happens. Because the focal length is out here. How do you deal with that? And then look at another one. Oh, well, I kind of give away it here. Where you put the object between the focal length and two focal length. Right? And what happens there is a magnification of the image and of the object. The image really a magnification of it, right? And that idea is used in projectors. So you have this little film, the light passes through it, through a lens, and then you get a big image on the screen, right? Projectors at school and long ago used to have in cinemas work like that. So here's a nice ray diagram, right? You follow those two ray diagrams?
Yes, sir.
They're all in your textbook, eh? They are one of you. Yes, and they're showing you here. Look here.
Sir, question, which textbook this is coming from?
I put it, these notes are on Moodle.
Moodle, yes, I saw.
Yes, it's a book called College Physics by Cotnell and Stadler. It's free online. But I'm giving you the chapters that you need. You know, if you see the book, it's couple, I think it's maybe 2,000 pages.
Okay, sir.
A whole lot of irrelevant things inside. So I chop out what you need and give. So remember I was telling you, what about if you put the object here, what will happen? Right? You wouldn't see if you were to, be looking here for the image, you wouldn't see it. So but if you put your eyes here, you will see a virtual image. And you make use of that when it comes to magnifying glasses. Right? And I have one right here to read on the screen. Right? So we have all the situations covered here, where the object is between the focal point and the lens, when it's between one focal length and two focal length, and then when it's beyond two focal length, right? And we have the application of it. In this case, we use it for magnifying purposes. In this case, we use it for projector purposes, right? And in this case, we use it for the camera, right? The camera. And well, we didn't go into much into the diverging lenses, But this is a ray diagram, right? This is a ray diagram. What a diverging lens actually does is make this object even smaller, right? I'm not going to go into much detail in a diverging lens. But of course, you wouldn't have who would have a glass like this where you have nice big writing looking small, right? It's not a practical thing. You usually want to write the small writing to look big, right? But this is just to show you how the ray diagram is, right? Yeah. Good. So we want to go to the lens equation, right? Wait, I think. Can you see here?
Yes.
They're calling it thin lens equation, right? Because when the lens is no longer thin, because of the properties of glass and the dynamics of light and so, the equation might not hold, So when the lens is thin, well, the equation holds, right? So this is the lens equation, 1 over, that's the object distance, plus 1 over the image distance is equals to 1 over f, which is the focal length of the lens, right? And the magnification is given by these relationships. The image height over the object height, or the height of, well, that's what they are, the height of the image over the height of the object. Or, notice, minus d, right? The distance of the image over distance of the object. This minus sign is really telling you whether the image is real or virtual, right? It doesn't tell you anything more. You don't worry with the sign so much. The magnitude of the number, if the magnification is 2, then you know the image is twice the size of the object, But if there's a negative sign, you mean that oh, sorry, I think, what did I say about the negative? No. The negative has to do with whether the image is upright or inverted. Sorry. I confused that with virtual and real images. Yeah. Right. So if the image distance is negative, notice you actually have a virtual image. And if the image distance is positive, then you have a real object, right? I think this is what you really want here. If the object distance is positive, right? Yeah. Let me see. Let me get this back clear. If the object distance is positive, no. Object distance is positive if the object is left of the lens. And if the object distance is negative, that is so if the object is right to the lens, it's a virtual object. This here is not usual, right? That has to do with repeated lenses and so, right? Yeah. So I think I was trying to clarify, if M is positive, that means that, well, the image is upright. If M is negative, the image is inverted. I think that's what I wanted to clarify. I think I have an example something. All right, yeah, look at this one. So let's take this one. This is a converging lens. Cameras usually have converging lens inside, right? So they're telling you a person is 1.7 meters tall, and he's standing 2.5 meters in front of a digital camera. The camera uses a converging lens whose focal length is 0.05 meters. They want you to find the image distance. That means the distance between the lens and the image sensor. And determine whether the image is real or virtual. And the B part says find the magnification and the height of the image on the image sensor, right? So this is like, those cameras you have in your phone, right? Yeah. So they're telling you that this optical arrangement is similar to that in figure 26.26a. I think they mean this. Let me just go back. I think this is what they're talking about, right? This is what they're talking, right? So you're actually getting an idea here that the object, the image will be much smaller. There's not going to be it doesn't make it bigger, make it smaller, right? So let's see the calculation. Let's go back to the calculation. So you use your, what do you want you to find? Find the image distance and determine whether the image is real or virtual. Good. So you use your formula, right? Rearrange it and so on. And you have to find the image distance, right? So that's D subscript I. So after you've put all of this inside there, right? You calculate, you get 19.6, right? So you have to flip that over. 1 over 19.6 gives you 0.0519, right? And they're telling you that this is a positive value. The image distance is positive. So what that means? The image has to be real. How else will whatever is inside the camera will sense it? There has to be a sensor in there, right? And if the image isn't real, what is it going to sense, right? So the image is going to be formed 0.051 meters behind the lens in the camera on a little sensor, right? And that image has to be real for it to be picked up by the image sensor, right? So that makes sense. The magnification formula, now we got the image distance, we got the object distance. And notice the magnification, you have negative 0.0204. Now remember we said the negative is really telling you whether the object, the image is inverted or not. And the negative tells you yes, it's inverted, right? But really and truly, the image is actually diminished, right? Very, very small, right? 0.02. So the person is 1.7 tall, but when it forms the image in the camera, the image is 0.0204 meters in size. Very, very small, right? The magnification is that. No, sorry, this is the magnification negative. So to calculate the image height, well, you use the formula. Well, here it is. Where is the formula? The magnification formula. Magnification is equals to the height of the image over the height of the object, right? So magnification. So from that, you can get the image height by multiplying the magnification by the object height, right? So the magnification is that times 1.7 gives you this very, very small number. So the image inside the camera is 0.0347, very, very small. I think I got that confused in the magnification just now. So this thing is actually less than 100th of the size of the actual image, right? How it actually diminishes the image. And this is another one. An image formed by a diverging lens, right? This is not a very, I mean, you don't see this in everyday life so much, right? So here it is. So let me get a little bigger. So you have some object 7.1 cm to the left of a diverging lens whose focal length is negative 5.04. The negative means that this focal length is in front of the lens, right? They want you to find the image distance and determine whether the image is real or virtual and obtain the magnification. So what is that going to look like? They refer to figure 26.29a. Let's see if we can find that. Give me 1 second. That's something like this, right? That's what you see. Yeah, that's what you see. Right? I don't know if you. This is what we're talking about. Right? So you already get the idea that, well, okay, the image is going to be virtual, it's going to be a little smaller than the object and so on, right? That's what you're talking about. Let's see the calculation. Right, so you make use of your thin lens formula, and you get that the image distance is negative 2.96, which tells you that the image is virtual and is located to the left of the lens. We saw that, right? Right? We saw that in the picture that I just showed you. And they want what else? Find the image distance and determine whether it's real or virtual. So we did that. The negative is telling you that it's going to be virtual, right? And the magnification. In the magnification, you put all of this inside and watch what happens. You get 0.417. And the fact that it's less than 1 means the object is smaller. The positive value tells you that the object is going to be upright. It is not inverted, right? And we saw that in the picture already. Right, so you won't have much of these. You don't see this much being applied in, your everyday life. Converging lenses are far more used than diverging lenses. Right? Keep that in mind. And that brings us to our whole treatment of refraction of light and lensing.